Oh, whenever you're ready.
Oh, okay. My name is Haley Bethera. My project is called a sliding block problem, and my advisor is Dr. Myers. In this problem, you're given a puzzle, and it has 6 vertices that blocks rest on, one central vertice with 2 arms extending to one of the exterior vertices. And so your goal is to discover whether a given arrangement of the blocks is solvable, and actually whether every arrangement of the blocks is solvable for a puzzle. I call this one Puzzle 1, and solving is just making a series of movements with that empty space to get the blocks from out of order back into their clockwise numerical order. And so for this one, it started out of order, and you can just see how it gets back in order. Yay, it's solved. Okay. And then to study this further, we need to look at what it means to have a permutation of 7 objects. So permutation of a set T is a bijective function from T to T. That just means that it is injective and surjective, or in other words, the input will map to the output. Every element in the input maps to the output once and only once. So you're not going to get an object, a set of objects going from like numbers 1, 2, 3, 4, 5, 6, and all of a sudden you get out ponies and stars in the output. You get the same objects one time. And so for this one, we see an example of a permutation. All the blocks are out of order, and you can see that block 1, it used to be in position 1, now it's in position 3. Block 3 is now in position 6. And these are all based off of positions, not the blocks with the numbers. The numbers just help you see that what was in position 1 is now in position 3. And this brings us to our notation. The top one is one I'm not going to be using so much for this presentation, but you can see that the input is lined up at the top row, and the output is in the bottom row, where 1 goes to 3, 2 goes to 1, 3 goes to 6. But the more concise way to notate this is a cycle notation right here on the bottom, where 1 goes to 3, 3 goes to 6, 6 goes to 5, all the way until you have 7 goes to 2, and then back around 2 goes to 1. And sometimes the cycle notation isn't just one continuous cycle. You have what are called transpositions. They don't have to be transpositions, but these are, because you see that 1 goes to 7 and 7 goes to 1, so they've switched places. And I'm going to show you a little bit more what that's like on the puzzle. So to achieve the transposition 5, 6, we actually, because the puzzle has limitations, we have to do all of this here to be able to switch just the blocks 5 and 6. And so to see that, first we're going to show 1 and 7, then positions 1 and 6. Oh, by the way, the middle position is 7. Now we have 1 and 6, and then the rest of them just follow. And these are all not disjoint, meaning that they're connected, and the order in which you do them is important. Okay, so now we're going to look at some moves that I've defined as alpha and beta, and these are just moves that are common, and will help us prove that this puzzle is always solvable. So first, if your center position is not empty, we want to show that you can make it empty, and all you have to do is move the empty space to either position 1 or 2, and then all you have to do is transpose the empty block with the block in the center, and now the center position is empty. So now we can always assume that to be able to do the moves alpha and beta. Now beta is this right here. It's a clockwise rotation of the blocks. See, now you have 1, 2, 3, 4, 5, 6, but it's just all rotated one space clockwise. Beta inverse is just the opposite, and you can see it undoes beta. And then alpha is a switching of the objects in positions 1 and 2. So is puzzle 1 always solvable, or is every permutation in puzzle 1 solvable? So is puzzle 1 solvable? Yes. And here's the proof. If you just need to make sure first that the empty block is in the center position, let beta equal this up here, alpha equal this, which is just the clockwise rotation of elements and the switching of elements in positions 1 and 2. And we're going to use this theorem that says every permutation is a product of transpositions. So we're going to look at all the possible transpositions in puzzle 1, which is right here. And this is using alpha and beta to show that every transposition in puzzle 1 is possible. And I'll show you a little example. How about 3, 4? We do beta 4 times, and then we do alpha, and then beta 2 times. And now it's back in order, when at first it had 3 and 4 mixed up. So looking back at this chart, you can also see I've ordered it so that the difference between, well, the first number in this transposition I've named A, the second number is B. The difference between them, when you arrange it, you can see a pattern in the number of alpha and beta moves that you need. And from that, I was able to make a generalization where you let the combination of moves alpha beta equal gamma, and then the combination of moves alpha beta inverse is mu. Then the transposition AB can be achieved by this expression right here. And I've just shown an example, 3, 4, you get beta -2 beta squared, and that's actually the same as beta to the 4th alpha 2 because you only have 6 positions, and so moving backwards 2 positions is the same as moving forwards 4 positions. So, in this proof, every transposition of the elements in puzzle 1 is possible. We showed that in the table. So that tells us that every permutation is possible, since permutations are composed of transpositions. So puzzle 1 is always solvable. Now we're going to look at puzzle 2. Is puzzle 2 solvable? No. This is the logic that you can follow for that. Permutations are products of transpositions. A permutation can be written as either an even number of transpositions or an odd number of it. So we call those even or odd permutations. For example, 1, 2 is odd. It's just one transposition. 1, 2, 1, 7 is even. And that's what this looks like here. So to be able to prove that this puzzle is not solvable, we need to show that some of the permutations are not solvable. And we're going to do that. Color alternating vertices black and white. Now you can see that when you have blocks on here, if the empty space, first of all, we're considering the empty space because no matter what permutation you have, you always have to move the block that's adjacent to the empty space. Every transposition you do is with the empty space. And also we know that to solve the permutations, we always have to get the empty space back in the middle so that all the blocks are on the outside. So that's why we're just focusing on the empty space. You can apply this to any of the blocks that you want to. But 2 cases, empty space starts on a white space or it starts on a black space. If it starts on a white space, you see that the only other spaces it can move to are black. If it starts on a... Okay, so to do 1 move, you go from white to black. To do 2 moves, you go from white to black to white. So even numbers of transpositions go from white to white, odd numbers go from white to black. Similarly, if you start on a black, you go from black to black with even numbers, black to white for odd numbers. So our conclusion for that is even permutations are only solvable if the empty space starts on a white, and odd permutations are only solvable if the empty space starts on a black. So this one is not solvable because empty space is on a black, but we need an even number of transpositions to solve it. And similarly for the odd permutation here. Alright, so, but if we do start on a white, are all even permutations solvable? And we're going to show that with AN is called the alternating group of degree n. It's just the set of all even permutations. And the different pairs that we're able to achieve with this, for the puzzle, A, B, C, and D are going to be the numbers 1 through 6 that are talking about the different positions on our puzzle. And you can either have transpositions in which, for the pair transpositions, you have 3 different elements or all 4 elements are different. And they can each be written as a 3-cycle or a product of 3 cycles. Here. Alright, so let me just explain this right fast. We have here A goes to B. And then, oh, I did not, okay, that's wrong. We're going to look at this somewhere else. Okay, actually, all that's wrong with it is that it's just backwards. This should be ACAB. So first we show, no, let's look at this one. Okay. So first we have A goes to B. No, we can't look at that one either. I'm going to skip this for the sake of time. But anyway, okay, so every pair of transpositions can be expressed as a 3-cycle or product of 3 cycles. If we can show that every 3-cycle is possible, then, alright, so we have here a 3-cycle ABC. We can express that as a product of 3 cycles beginning with 1 and 2. These are the positions 1, 2, and this only works if A, B, and C are not equal to 1 and 2. If A, B, or C are equal to 1 and 2, then we can express them as this product of 3 cycles. But to show, if we're able to show that these 3 cycles are solvable, then going back to here, we know that we can make any combination of 3 cycles to achieve any pair of transpositions, which achieves any even permutation. So we need to define a new alpha and beta. They're very similar to puzzle 1, but we see that alpha achieves this rotation here, and beta achieves, it's kind of like a counterclockwise rotation, but you're skipping space 2. And all of these 3 cycles are solvable with these products of compositions of alpha and beta. And so puzzle 2 is solvable for all even permutations, in which the empty space starts in the center. Okay, and then puzzle 3, I wasn't able to get into it very much this semester because of time, but according to the paper that I referenced for this problem, it's not solvable. No 2 cycles or 3 cycles are solvable, and you can kind of see that already, that the only really possible moves are moves involving 4 blocks at a time. But again, puzzle 3 is not solvable. I did have time to make a generalization of puzzle 1, and this is kind of based off of what I showed earlier in the proof, but this time it's saying for any number of vertices, we can do this product of moves of alpha, gamma, and mu and beta to solve the puzzle for a given transposition. So for example, this pentagon here, we just show A and B, for example, are 2 and 4. That just means that we want to transpose 2 and 4. Then we plug in here, N is the number of vertices on the puzzle, so we have 5 vertices. So we plug in our numbers A, B, and N, and we get out that we need 3 betas, 1 gamma, which is alpha-beta combination, 1 mu, which is an alpha-beta inverse combination, an alpha, and then 2 betas. And then we've switched 2 and 4. And that'll work for puzzles of any amount of vertices. And because of that, because we know that we can achieve any transposition in the puzzles of any amount of vertices, then puzzles of this type where you have positions 1 and 2 connected to a center vertex are always solvable. And that's the end of my presentation. If I wanted to look into it further, we could consider generalizations for puzzles 2 or 3, or work on proving that puzzle 3 is not solvable. Any questions?
It's not really a question, it's a comment. The thing that you've been calling gamma every single time is lambda.
Lambda.